Hi folks, it's Mr. Robeson here. We're getting towards the end of things, so we're doing linear regression here. We're going to start doing inference for linear regression, so we're going to do a little bit of review first, and then we'll go over what the conditions are, which are a little longer and a little more complicated than the other conditions for the proportions and for means. All right, so first up, linear regression. Let's see, do we remember how to do this? So a random sample of 10 high school students produced the following results for the number of hours of television watched per week and GPA. So we've got number of hours of television watched per week and GPA that we're comparing. Can GPA be predicted by hours of TV watched? Look at the scatter plot of the data. All right, so here's our data. We've got TV watched and we got GPA. So we want to predict the GPA. So our TV watched is going to be our X. Our predicted GPA would be our Y hat here. So we'd put both of these into lists, say L1 and L2, and then we'd look at the scatter plot. So let's pull up our calculator. I've already done the work of putting them into lists. So stat, edit, and there they are, L1 and L2. So now if we go to our stat plot, and we turn the first one on, we turn it to the points, we put L1 and L2 in there, we can pick whatever mark we want for dots, and we can pick whatever color we want on this calculator. Some of your calculators don't have that. And then we want to zoom 9 to get a good look at it. And there's our points. Looks like they're lining up pretty well. We definitely don't have any outliers. Nobody's way off of the pattern. We may have one influential point back here. The 0, 3.8 may be influential. But if you want to say that or not, you can or not. It doesn't really matter too much. All right, so what do X and Y hat stand for? So X is the hours of TV watched per week. And Y hat is the predicted GPA. All right, find and interpret the slope of the least squared regression line. So we need to do the regression analysis on this data. So we go to stat, go over to calc. So it was only calc. I know we're so used to going to test. And when we usually go with number 8, we could also go with 4, but 8 is usually what we go with because it gives it to us in the order we want. L1 and L2, yep, that's what we want there. And go down to the bottom and select calculate. And voila, there it is. So it tells us our y-intercept, our A is 3.89. And our slope is negative 0.072. So we get negative point, so our slope, which we use the letter lowercase b for, is negative 0.072. So there's finding the slope. Now we need to interpret the slope. All right, so remember what we say, for each increase of 1, and then whatever our X is, so it'd be hour of TV watched per week. We predict, remember, because this is the predicted Y, on average, and we could have put the on average really anywhere. We can put it at the very beginning, we can put it in the middle, we can put it at the end, but it needs to be there somewhere. We predict on average that GPA, and it's negative, so will decrease by 0.072, and the units here are just points, grade point average, so points. And there we go. And there's our interpretation for the slope. All right, next we want to find and interpret the y-intercept. All right, so the y-intercept, the A was 3.89? 89, yep. All right, so that means that if X is 0, the number of hours is 0, the y-intercept, or the GPA we predict, is 3.89. So for 0 hours of TV watched per week, we predict, on average, a GPA of 3.89, and I guess we could say 0.0. I know we don't usually have a units on that. All right, so we could write our equation here, if we wanted to, as the predicted GPA would be equal to 3.89 minus 0.072 times the hours of TV. All right, but that's how we could write the equation, just like that. We don't have to use x and y bar. We can just use the words, which is often easier, just using the words. Find and interpret R, the correlation coefficient. All right, so where's our R? It's the bottom one here, negative 0.962. So R equals negative 0.962. All right, so if R is close to 1 or negative 1, that tells us we have a strong relationship. Let's see, linear we really get from looking at the graph. What else do we have from Duff's? Direction, oh, negative. All right, so remember, go back to Duff's. That's what we'd use to describe linear. It was direction, unusual, form, linear, and strength, strong. All right, because it's close to 1 and it's negative, so we're going down. So there's a strong negative correlation between GPA and hours of TV. I suppose I should say watched here. All right, if we wanted to say linear, we really have to get that from the graph. So we have to look at the graph. To get linear, we have looked at the graph, so we do know it's linear, but that's really where that's coming from, not necessarily from the R. And remember, the R will always have the same sign as the slope. Both of them are negative, or both of them are positive every time. Find and interpret R squared, the coefficient of determination. So that was the other guy there, which is 0.9257, so 0.926, I guess. And we usually write this as a percent. So that'd be 92.6. And then we would say 92.6% or 92% or 93% of the variation in whatever our y is, so GPA, we always do it with context, can be explained by, we can either say change in hours or just hours of TV watched. Whatever our X stands for. And there we go. All right, so it's always talking about the variation there. The percent of the variation in Y can be explained by X. All right, so there's our review of linear regression. Whew, lots of stuff there. All right, next up, so for inference, because that's what we're working towards inference. We have conditions we have to check that have to be met for us to do inference on linear equations. All right, because really, we're always working with a sample here with a certain number of observations, say n observations, between your x and y variable. So remember, your x is your explanatory, x for explanatory variable, and y is your response variable. That's what you're getting out, your output. Our goal is to predict the behavior of y for given values of x. All right, so we're really, that slope that we're getting is just a predicted slope. It's actually just the middle of a confidence interval for some sort of slope. All right, so the conditions, the easiest way to remember this is it makes the acronym LINER, L-I-N-E-R. So linear, there must be no pattern in the residuals, and x and y needs to look like a line. All right, so we may need to look at the residual graph and the actual graph to get both of those. Independence, that's still our 10% condition. Normal, so the normal condition here is we want to look at the histogram of the residuals. We want it to have no outliers and to be not strongly skewed. All right, the E, equal standard deviation. So if we look at any value of x, any particular value of x, the y should be roughly symmetrically or uniformly distributed at that x value. The way we check this is we look at residual plots, and we should have equal amounts above and below the x-axis, or the zero residual, for all x values. So it should have the same amount above and below. So like there should be some above, like here's the line of best fit. There should be some residuals above and some residuals below. It should be about the same amount between both of them. And random, we always need random, all right? We want unbiased samples, so we need some sort of random sample or a randomized experiment. All right, and we have, remember, different symbols. Remember, we usually use Greek when we're working with population. So we don't use y, though. We use the mean y value. So again, because there's going to be points all over the place, so the middle y value would be the mean y value. So the mean y value is equal to alpha plus beta. So this is beta times x. So beta is our true slope. All right, so beta is the slope that we are going to be looking for with the confidence interval. So we're going to do a confidence interval for the slope. All right, so here's just checking the conditions. So remember population, we've got the Greek sample where you're just using the x and the y hat. B, the slope B from the sample is a point estimate for the slope of the population line, beta. Our y-intercept A is also a point estimate for our y-intercept alpha, but we usually don't do a confidence interval for that. We usually just want to know about the slope. All right, so here's our example here, then we're going to check our conditions. So a class did an experiment using paper helicopters, which we probably would have done if we were in school right now. After making 70 helicopters using the same template, students randomly assigned 14 helicopters to each of 5 drop heights, 152 centimeters, 200 centimeters, and so on. Teams of students released the 70 helicopters in a random order and measured the flight time in seconds. The class used computer software to carry out a least squares regression analysis of these data. Here are a scatter plot. So here's our scatter plot. Residual plot. So here's our residuals. And a histogram of the residuals. So this is our histogram of the residuals. Check whether the conditions are met for performing inference about the regression model. All right, so usually if they give this to you on the AP exam, they do give you the graphs. So the graphs are pretty much always there if you have to do this on the AP exam. All right, so we're going to go through liner. So is it linear? Well, we can look at two things. So we're looking at the scatter plot. That seems to be linear. And the residuals doesn't seem to have any pattern. So the scatter plot appears to be linear, and there is no obvious pattern. I know there's a lot of writing going on here in the residuals. All right, I, independence. All right, so each drop is independent of each other drop. So each helicopter is independent. And n equals, how many times do we drop this? 70? All right, it's definitely less than 10% of all possible helicopter drops. All right, n. Let's see, so that was the normal one. So we're looking at the histogram here, and we want no outliers and not strongly skewed. So we say the histogram of the residuals has no outliers and is not strongly skewed. All right, so remember, a little bit skewed is not really a problem. We just need it like to be ridiculously skewed would be a problem. All right, LINE. So that's the equal standard deviation. So let me go back. I know it's the residuals. We're looking for the equal amounts above and below. Let's see, what's the actual phrase I'm supposed to say here? Oh, I have effects here. Residual plot, equal amounts above and below the x-axis. All right, for each x value. All right, so for each x value, the residual have an equal amount above and below residual equal to 0. So let's say here's the line residual equal to 0. And you can see like above and below, above and below, above and below, above and below, above and below. Like it doesn't have to be perfect, but we have some above, some below for each one. And it looks like we've got about the same total amount below here as we have for the same total amount above here. All right, so that works out. And so we had some sort of a random order. All right, so we were, helicopters were dropped in a random order. All right, so there's all of our conditions, our linear condition, our independence condition. This was our normal condition. Probably should have written normal here. All right, equal standard deviations and random. All conditions checked, so we would be able to do linear regression for this and inference for this. We'd be able to say, oh, what's the slope? What's the interval for the slope for this? All right, so that's it for the first one. Next one coming at you next.